Hello, this is Jenna Zahid, and today I'll be presenting Lab 2. So, the purpose of this lab to observe the kinematics of a freely falling object on the surface of Earth and study the forces that affect its motion. And the fundamental physics concepts we have explored are drag force, gravitational force, and terminal velocity as the object experienced them, and then we compared them to the computational models we had. And also through the lab, we learned that freely falling objects on the surface of Earth that are falling outside of a vacuum are normally faced with a drag force, which causes them to move with the terminal velocity. So for the physics concept you have discovered, it's mainly Newton's second law of motion, which is F equals ma. So with drag, we have the force bv, and fg minus bv equals 0. Therefore, there is no acceleration and there is a terminal velocity. And when there's no drag, we only have mg equals ma, and our a is just g. So here is the graph of the motion of the ball that we have saw. So we can see the slope of the xt graph is straightening up and it's becoming linear. This is because we're approaching a terminal velocity. And then we can see that the average acceleration is 9.8 because of g, but then drops to 0 as the drag force is experienced. For the computational models, with no drag, we have assumed that there's a constant gravitational acceleration. That's true for both. This is because Fg is an acting force. We assume that there's no air resistance in the no drag model because it's falling down in a vacuum, but there is air resistance present in the drag model. And there are no external forces because there's no air resistance for the drag model, but there is, but for the with drag model, it's dependent on velocity and how fast the object is falling down. For the initial conditions, the object was dropped and the initial velocity is just 0, and it was from a 1 meter point. For the system, it's the ball and the surroundings are earth and air resistance. For the details of the experiment, we just took a ball and we dropped it, and then we measured the height to be 1 meter before dropping it, and then we tracked it using tracker or the software we use, and then we concluded the results. Our materials are the object timer, a measuring tape or the meter stick, and the platform where we performed the experiment. For the coding part, so I changed the mass to 25 grams to reflect the actual mass. And then for B, I use 0.47 because that's the drag coefficient of a light small ball freely falling. And I also used B equals 0 in order to represent the situation of where it's falling with no drag. And then I added the drag force, which is B times V, to the F net. And whenever B is 0, then the drag force added would be 0, and that would be accurate for both models. This is the comparison between the computational models and the actual object that was falling. So the actual object was closer to the model that had drag. This is because the real object was experiencing air resistance because it's not placed in a vacuum, and that was the biggest difference between the vacuum model and the object that was in real life. So here are the graphs of the computational models. So with drag, we can see the terminal velocity and we can see the linear slope of the xt graph. But for without drag, we can see that there's a constant acceleration of 9.81. For the physical errors, there might be measurement uncertainty because we use the meter stick. There might be environmental factors like the air resistance changing, and it's not a constant coefficient. And also for the reaction time when I was manually tracking the object's motion. So for the results, the key findings was that there was a terminal velocity, there was a force balance, and in relation to drag, the drag force was the one that was causing the terminal velocity, and that's why the ball stopped accelerating at one point. For the interesting conclusion questions, so velocity times time was predicted with our models without drag. Terminal velocity means that it reached like a constant velocity because the forces are balanced and it was at equilibrium. This is what we found out. Terminal velocity happens when the force of drag pointing up has exactly balanced the force of gravity pointing down. This means that the net force is 0 because that the forces are balanced out. And for the what if, this is the terminal velocity would be the same because no matter what the initial velocity is, the resistive force that the object is experiencing is the same unless it was falling down with an initial velocity that's in the y direction, then it would experience more resistive force because objects falling down with a greater velocity experience more resistive force. And in conclusion, we saw that freely falling objects in real life are more related to models with drag, and this aligns with our theoretical predictions. Thank you.